Okay, this video we're going to continue we're looking at matrix multiplication. We're going to just practice working with it a little bit and go through the basic identities and properties that it has. So let's do that. And so like in general, when I'm introducing some new operation like this, I want to compare it to what I already know and think about it. And so when I'm thinking about a multiplication operation, I think about those kinds of identities that I know, like x times y is equal to y times x, x times 1 is equal to x. So these kinds of things, right? Associativity, commutativity. So we'll just kind of like work through those and think about them. One of them is that the identity, can you multiply a matrix by 1? And you can. So in general, if you have any m by n matrix A, you can multiply it by the identity matrix and get back A. Identity matrix, remember, it has 1s down the diagonal and 0s everywhere else. And that's a good one, again, to just like work through if you're curious. One thing to think about here is that for this to work out, this has to be the n by n identity matrix. Going the other way also works. So if I have I times A, that's also going to be equal to A. But this time it has to be the m by m identity matrix, right? So, but yes, so the identity matrix works kind of like as a 1 in matrix world, right? And the same is true, of course, of a 0 matrix. It should be, this one doesn't come up as much. I keep wanting to put a vector on there, but you know, if you put the m by n 0 matrix on here, then of course you would get 0 out. That one I think doesn't come in as handy, but you know, useful to know. Okay, so that was identity. Associativity also works as we might expect. So if you have 3 matrices that you're multiplying all together, like A times B times C, you can do it in either order. So A times B is equal to A times B times C, like this. And there's some interesting sort of computational or optimization facts for that. Why do I keep losing it? Which we'll come back to in a later date. One thing, just for now, one thing to be aware of is that, again, the units all still definitely have to line up. So if this is m by n, this guy has to be n by p, and then this guy has to be p by q, whatever it is, right? But then if they do all line up, then you can do that. What about commutativity? So with regular numbers, scalars, real numbers, you can do something like this, but you cannot do this with matrices. As a general rule, it is not true. Of course, you could construct special matrices where it is true. Like, for example, if you do identity matrix times the identity matrix, where they're both, n by n identity matrix, then yeah, it doesn't matter which order you do it in. But in general, no, that is not true. And again, our units help us out here. So, so if you think about like, if you think you have some m by n matrix A and some n by p matrix matrix B, then those two things, if you flip them, then it's not even going to line up, right? You have n by p times matrix A, which is m by n. So this is only going to work. It's only even possible to multiply them both ways if p and m are the same, right? So if they were square matrices, then maybe but even then it's not true in general. Like even if you had 2 by 2 matrices, that it is not in general true that you can commute them. You just can't overall. So that's just, again, multiple x's exit all out, doesn't work. Okay, fine. But okay, so we said associativity works. What about distributivity? So distributing by a scalar works just fine, works as you might expect if I have some scalar value alpha. And remember, scaling it by the matrix, we just multiply every element of the matrix. That's going to be the same as doing it like this. You can move it inside there. And okay, distributivity also works. So if I have matrix A times B plus C, that's the same as AB plus AC, and that will work out. That will work out as we might hope. And in general, if you have block matrices, so let's say I have a matrix. I have a matrix that's made up of 4 submatrices, A, B, C, D, and then I have another one that's E, F, G, H. This works, and you do a matrix multiply here. This works exactly as if it were elements in a 2 by 2 matrix, or in general an n by n matrix. So this output matrix here is going to be AE plus BG. This one down here is going to be CE plus DG. This one's going to be AF plus BH. And this one's going to be CF plus DH. And again, so these are matrices. So this now is like a smaller matrix product, and then two smaller matrix products and a matrix addition. But it works just as if it were individual scalars and you were doing the inner product of them. So that's really nice. That comes in handy if you often want to like break down or decompose a matrix for various reasons, right? And that works as you'd expect. Okay. So those are the big ones. I'm trying to think if there's anything else in particular that I want to make sure that we cover. Check my notes. Okay, so one thing I did say I was going to come back to, or maybe think more about, is that when you have where'd my distributivity go? Okay, so over here, whoops. I've got my case where I'm multiplying 3 matrices together, right? And I have an M by N and a N by P and then a P by Q. Let's actually copy that whole thing over, and we'll do some work with that guy. Okay, cool. So there's 2 different ways of doing this here, right? This one is M by N, this one is N by P, this one is P by Q. These could be potentially, although they're very similar, although they will always get you the same answer, they could be potentially very different amounts of computation. So for example, let's say that P was some very small number. Let's say P is whatever, 10, but these other ones are all in the thousands, right? You want to do this, the smaller one, well, maybe I should go through it. Okay, well first actually let's talk a little bit about the computational complexity of this whole thing, right? So in general, we said we have something like we've seen this guy before, some cross k, aik, bkj, right? Where I is running through n, k is running through, oh sorry, I is running through m, k is running through n, and j is running through p. So that means the overall work of this thing is proportional to all three of those. In particular, like this inner product that we're doing, you can think of it kind of like if you're writing it in pseudocode or something like that. This is saying for each I, so for I in 1 to m, and then inside that for each j in 1 to n, and then inside that for each k in 1 to, oh, j was supposed to be p. For j in 1 to p, for k in 1 to n, c ij plus equals a ik times b kj, right? So this is the pseudocode algorithm for matrix multiplication, this kind of triply nested for loop, right? And in general, it's going to take approximately m times n times p operations to do. Technically, so here I've got I've got the scalar multiplication, and then I've got the add. I'm adding that product into whatever was in Cij before, so it should actually be like 2 MNP to do that. But yeah, so in general that's the case, right? But that means if some of them are bigger or smaller, then you might want to try and avoid doing that work. In general, you want to try and avoid doing the larger work. And so in this kind of an example, like we were talking about before, if say P was small and M and N and Q are big, if you do this one first, if you do the left one first, then this P, so now I have MNP work that I'm going to do, right? And then I have to do later, this guy is now an M by P matrix, so now I have MPQ work that I'm going to do, right? If I do it on the left-hand side way. If I do it on the right-hand side way, well, now I'm going to do N by P by Q work because I'm doing this one over here. And then I'm going to do M by N by Q work when I do the A one over here, right? So if I said P is much smaller than the others, then I would prefer the one on the left because it's got a P on both sides, and I'm avoiding doing this one, the MNQ, because that one is going to be, in theory, much larger and much more work. So I want to try and sort of minimize that. And if you have a long chain of multiplications, you could do a ton of work. You could save a ton of work by figuring out which is the most efficient, but it sort of becomes a combinatorics problem. Which units are you going to reduce and so on. Okay, that ended up being a little more of a side than I wanted to, but I think it's worth it. Okay, so overall, this is just thinking about what you can do as we're going to sort of like work through problems with matrix multiplication. One, the identity matrix works like a 1. You can multiply it anywhere. Associativity works. Distributivity works. Commutativity does not work. And yeah, those are the. Oh, and then transpose. I made a whole other video where we talked about. Let me zoom in here a little bit. I made a whole other video where we proved this fact, but I just want to have it here in this video also. If you have A times B transpose, then that is equal to B transpose A transpose, like this. And like I said, I proved that fact and talked a little bit more about it in the other video, so I'm not going to do that here. But that does work, and these things all can sort of like work together, right? So so if you have, I'm trying to think of a good example off the top of my head where it would matter, but well, okay, let's do the distributing one. So let's say I have A times B plus C, right? And then that whole thing is transposed, right? Then I would get, if I wanted to do the distribution first, I would get AB plus AC transpose, which is equal to C transpose A transpose plus B transpose A transpose. Or I could do it the other way first, where I go B plus C transpose A transpose, and then do the distribution after that. Oh, and one other thing. I keep thinking of one more thing I want to show, but you know, we matrix vector product. So if you have like AX transpose, where X is a vector, it distributes in the exact same way. So you end up with something like X transpose A transpose, right? Which means, let's say you're doing the inner product. So let's say I have like Y transpose A times X, right? So Y is a vector, A times X is a vector, and we're doing some inner product between those. We could, for example, do like, use the associativity rule to rearrange to do Y transpose A times X, like that. And if I wanted to, I could transpose those also. That this is, for example, A transpose Y transpose X. So yeah, so I transpose both. I transpose the inner product and the outer, and I get this piece here. This one's kind of weird because I'm actually, like, if you're thinking about what I'm, like, algebraically, what I have to do here is to do something like Y transpose A transpose X, because A transpose of something is just A. If you transpose it and then transpose it back, you get the same thing, right? And then I'm going to distribute this transpose into here to flip these around to get A transpose Y, and then I just have the outer transpose, and that's how I get that. So yeah, so this is just kind of an interesting one because it's showing that if you're doing the inner product of something, you can move that matrix vector to the other side. Okay, all right. So this was more just like practice with it, practice thinking about the identities. Go through these, try a couple examples. I think it's good to work through these examples.